We have talked about this at some point in a very casual way, I would say. What is it?
It means that the material properties change with the direction?
Exactly. And what does it mean in elasticity? So that is a general definition. What does it mean for us in this class?
Young's modulus is dependent on direction.
If you want to make it more generally, like the deformation behavior is orientation dependent. I won't call it just Young's modulus because some other modulus, it can be something else and not necessarily. So that's why. So perfect. So in elasticity, when we say anisotropic elasticity, that means that deformation behavior is orientation dependent. Just to make sure, what is heterogeneity?
Non-uniformity of material elements, material properties. Non-uniformity.
I want more technical, more specific.
At every point in space in the object, it has homogeneity, is it's all the same. Heterogeneity is it's different everywhere.
Exactly. So we both are correct, but more specifically, the material properties are not a function of a space. So just there can be some dependence on both, because of course if the material is very different, then probably in the orientation you may have, but not necessarily, right? So try to have these two concepts always. It's like precision and accuracy. You need to always be very careful about the terms you use when you talk about it. So now my question is, why do we care? Why I'm presenting this as a special topic, and why I'm saying this is useful? Is this useful? So what does it mean? It means that when I say deformation behavior is orientation dependent, it means that you can have a situation if you take a sample from the same material one way or the other, you may get a different stress strain behavior. That's basically what it is in lay words. Now, can you think about natural materials which have this kind of properties? I give you a few a few seconds. I heard something correct coming from Kingsley's direction. Wood, of course. Is there anything else?
Minerals, fabrics, and orientations.
Exactly. Minerals in general, any solids which have crystalline structures, they have this kind of behavior. Minerals, rocks, right? So how about, let's call it engineered examples? I expect answer from one particular student right now. Composites, right? Composites, because fiber reinforced composites. So Tom, since this is your particular student, this is your research, and since there are students in this class that I know their research is completely different from what you are doing, could you explain very quickly what a composite is? When I say fiber reinforced composite, what that is?
It means that you've got many fibers, usually of the same material, that are oriented in planes where they're all in the same direction. And then what keeps those fibers together is some sort of matrix which is usually like a rubber type material. So a good example of it is like concrete, reinforced concrete. Rebar is like the fibers, concrete like the matrix. But think about that on a much smaller scale. It's like a more package. So like ballistic armor is a fiber reinforced composite, Kevlar or something like that.
Does this make this clear for those of you who are not familiar? And where does this, so if what Tom explained was not as clear, let's look at some examples here. So to the very right, this is what Tom was talking about, when you have fibers in two different directions, and then it becomes obvious that the material properties would be different in different directions. And then you see some atomic structures which also translate to anisotropy, because if you go along different directions, the number of atoms that you are going to cross will be different, the number of boundaries. So basically this anisotropy comes from microstructure. This is what I want you to get into. So everything comes from microstructure, and you will see it in macroscopic behavior like stress-strain curves. Now, the good news is a lot of materials, whether natural or the composites, they have symmetries, which makes everything easier. And what we want to do today is to look at the elastic tensor that we talked about ages ago in this class and see how it would look like for different symmetries, something very useful in a lot of applications. So now let's go back to what we were before. So we are still, everything is elastic, linear. So let's look at the Hooke's law, the generalized Hooke's law. So if you remember, the generalized Hooke's law we wrote it this way. I know some of you are not happy to see these notation showing up again, but that's very useful here. That's actually where this is, you will see how this is useful. So do you remember, so hopefully you remember what Cij KL was. First of all, what's the nature of this object? It's a fourth order tensor. And in general, how many elements it would have, like how many constants? 81. But what happens is, we talked about some symmetries, right? So if you look at the symmetry of a stress, you can switch I and J. If you look at the symmetry of the strain tensor, we can switch K and L. So this is because of the symmetry of I hope you still remember this notation, all of that. That would be my great hope, if when you next semester or in your professional life, that you actually feel comfortable a little bit better. And then we looked at the energy, and if you look at the energy, if everything is differentiable, then you could also switch Ij and KL because of those second derivatives. If you don't remember, look back, this is in your notes, long time ago. And if we take into account all these symmetries which have nothing to do to microstructure, I haven't talked about microstructure at all. I'm just looking at the properties of a stress, a strain tensor, and the energy. How many constants we will have? Do you remember that? So 81 will be reduced to I give you a couple of seconds someone who hasn't, I feel like there is a disparity. Like here, I hear a lot more than I hear from the other side, right and left. How many? That would mean that it becomes symmetric. If a tensor, fourth order tensor is symmetric, how many elements do you have? 6.
No, fourth order, that's 21.
21. Eventually 6? Why? There is nothing right now to say that it is 6, right? It's 21. So, now, something that we didn't discuss before, and now that we are looking at this more carefully, and you may come across in your applications, is sometimes people would like to express the strain in terms of a stress, So like this, and then it will have a similar form. What do we call this tensor? I heard something correct. Compliance tensor, right? It's elastic. Compliance tensor. Some of you have dealt with this in different situations, and without going through it, this tensor has the same symmetries as CIJK. One is they are related. Maybe I write this down. So S has the same symmetries as C. Okay. Now, something that we did not talk about, and it's sometimes useful, is the so-called Voigt. Is it happening again? End of the semester for my surface and everything in it looks like situation. I cannot explain. I don't use Windows machines anymore, so I cannot explain what happens to them. It looks very random to me, and from time to time they get tired or warmed up or something to that end. So there is another representation which is called Voigt. Sometimes it's called Voigt matrix notation, or you may have heard about it as contracted or reduced form. Especially engineers like to do that. They feel uncomfortable around tensors which have 4 indices. So the way to do this is as follows. So you have so the same tensor, you are going to have, instead of writing it in the tensor form, you are going to write it in a matrix form. And then here you have sigma xx. That's typically how it shows up. Sigma zz, sigma yz, sigma zx, sigma zz. And here are exx, eyy, ezz. And remember this engineering strain. So typically this is with 2 times shear strain, because we have seen this before. Something is wrong here. No, yz, zx. No, this is wrong. This is xz. This cannot be. Oh, it's xy here. Okay, got it. And then you have C11, C12. So you just use 2 index like that, and then you have and then this is symmetric. This is how I would write the symmetric ones. So sometimes you will see this with I and J capitalized in a lot of textbooks or in a lot of papers. And this is symmetric. So you still have, of course, that 21 elastic constants. So what I like to do is, so we are going to get back to this. Is it the second one? Maybe I started. I don't think it will fit here. I start a new page. I want to write this in terms of our coefficient 1, 2, 3, 4, like with 4 indices. Because then for every symmetry I want to go back and write the corresponding elastic tensor on the same page, because that would be easier for you to visualize. So you can organize it the way you like. So I want to write this Cij. Now again, I mean, writing C11 to C16 is kind of obvious what it is. I want to write it in terms of Cijkl. So this has these components: C1111, C1122, 1133, C1123. And your book has some mistakes here. So if I copy everything correctly from my notes, this is the correct version. And then you have C22. So 1 1 1 1 2 2 1 1 2 3 3 1 1 2. Okay, this is good. C22 2 2. C22 3 3. You will see why this is important to realize what is what in this. C22 3 1. C2212, C3333, C3323. It's not very obvious what is 2, what is 3 here. So C3323, C3331, and C3312. C2323, C2331, C2312, C3131, C3112. This is 1 2. It's hard to write a little bit. C1212. And then this is symmetric. And if before you were not convinced about 21, you can count, and there are 21. Right. So the purpose today is that I want all of you after this class never make mistakes in terms of elastic constants, because as a graduate engineer or scientist, I think this should be, you always have to know what's going on. So, and this is what we want to do today, carefully. So now I haven't assumed any kind of symmetry. So this is for a homogeneous, if things are constant, if all these C's are constant, they don't depend on location, this is a homogeneous, but it is fully anisotropic material. And you have a maximum 21 constants. Those symmetries have nothing to do with microstructure, nothing to do with that. Those are just symmetries because the stress tensor is symmetric. I've shown you this before. A strain tensor is symmetric, and things are continuous, so you can change the order of derivatives when you calculate energy. It has nothing to do with microstructure. Just please remember that for the rest of your life. It has nothing to do with microstructure. This is important, right? Now, I keep this matrix on this page for the reasons that you will see. And I want to now talk to you about material symmetry, because fortunately, most of our materials, even the ones that you mentioned, they have some sort of symmetry, and that is the fun part. Now, I want us to use the knowledge we gained in this class and decide how many constants we will have for each, instead of just memorizing it like you have done probably before. Am I right? A little bit? Okay. So, we start with what I call material symmetry. So the good news is we don't have to deal with 21 constants most of the time. Even in complicated materials like rocks or composites, as a matter of fact. So there is the so-called Neumann. My pronunciation may be very German, but I don't know how you would pronounce this. Neumann. Okay. It's called Neumann principle. It's the name of someone. And this guy said that symmetry in material microgeometry will translate into symmetry in macroscopic properties, pretty much. And that's important. So it would correspond to identical symmetry in the constitutive response, which is what we care about. So it means that if you want to find out what type of response you want, you have to look deeper. You have to take a microscope and find out what's going on inside your material. So what do we know about symmetry? Do you remember from long time ago when I asked you once in a quiz probably how you would define mathematically an isotropic material? What did we do? What kind of material has CIJKL constant? Does that have anything to do with isotropy? That's homogeneous. So that's kind of where I like us to be careful from now on about. If it is constant, that quiz had that part too. So if it is constant, exactly, it is homogeneous. Now, what did we do about isotropy? someone who hasn't talked in the class before. Okay, let me remind you, there is something that I hope you all remember. Do you remember something like that? And believe me, one reason you remember because it showed up in the quiz. I'm a firm believer of what you recall is what you retain. So that's what people say. So I know that these quizzes have been painful. However, I hope that down the road you think about them as really a way to be motivated and looking. So we looked at this because this has a lot to do with orientation. So this is telling us that if we rotate, so we learned this in the context of change of basis. So if you rotate a basis, then you can get the elastic tensor in the other basis using this. So if, for example, the material is orientation independent, then it shouldn't matter how you rotate it. Everything should be the same. So if I take that prime off, that becomes isotropic. But this is the only thing we did last time. And what was Q again? Exactly, direction cosines. Which we defined as, you have it in your notes, so the cosine of the angle between pairs in the two different bases. We talked about this in the context of orthonormal basis and change of basis, long time ago. Now, let's take a look at some important material symmetry. Case 1. If the material has plane of symmetry, so now I take the case of having a plane of symmetry which coincides with x, y. So x, you can think about it as 1, y as 2, z as 3, and the plane of symmetry in my example, without loss of generality, would be, I use my best art so this is plane of symmetry. Okay, and actually, if you want to see something which looks, what's happening? Where is it? Oh, okay. I never understand. So this is how it would look like if I could draw it better, right? So the material is symmetric with respect to x, y. Now, how would Q would look like in this situation? Could you write Q? It's 3 by 3. What would be Q? So Q is what? The definition is the cosine of the angle between the new coordinate and the old coordinate. So the new coordinate, I mean this is now x, y, z, So the symmetry, z becomes negative z. So that's how you have to think about it. So x and y stay where they are, z is rotating 180 degrees, pretty much. Exactly, that's it. 1, 0, 0, 0, 1, 0, 0, 0, minus 1. Z is just flipped. This is not a real rotation, so I have to add, for this particular case, it's not a perfect rotation. You cannot get a right hand coordinate, I'm sorry. So 1 and 2 that don't change, that's why you have 1, 0, 0, 0, 1, 0, and z is just flipped. However, this works. Also, things a little bit are shaky here, but this is correct. Now, the question I have is, you have seen this formula before. What happens to Kijkl if you have this kind of symmetry? Now we have the knowledge to actually calculate it. So let's say, do one example. Like, what happens if I want to calculate what happens to C1122? Try to write C1122 prime and see how it is related to the previous, like in the how C1122 will change. You have the formula. So here it's CPQRS, or whatever you want. Check it out and see what you would get. So kind of to see what you have learned before, how you can use it. It's like this one again. It looks like it's been really a while. Yeah. Okay, that's in the right direction. Okay. Partial. Okay. Okay. So it looks like, I know it's, a lot of you have this. Yeah. So, what do we do here? So these Q's, the Q is up there, right? So what is Q1P? Is it, no, 1P is just one component. So how can we write it using mathematical notes? When I write it, you all say yes. So wouldn't it be delta 1P? Because if P is equal to 1, it is 1, otherwise it's 0. So that's the nice thing about those Q's. They're easy to work with. And then what happens? What does the delta do? Nice. Do you see what you have learned? So you immediately see that this component under this symmetry stays the same. Where it is equal to 3? Yes. No, I don't think so. Q13 is 0. So, nice, right? But there is a negative 1, and this is going to change some of the components. Now, to give you an idea of what components are changing, why don't we calculate C1, 1, 2, 3? And this one, I want you to calculate, please, yourself, because I think I know my alphabet, right? S. Wait to see. So this goes back to, it's 3. 3 has to be there because that's the third component. So I guess you all have, and this one becomes negative right? So you see, it's very easy to see what's going on. And now, I want to, if you want to think about these, what happens to the coefficient? So let me go back to where I told you I write this, and I go back to this matrix for different symmetries. Now you learn that some of the components are stay the same, some of them become negative. If they become negative, what does that mean? Maybe I should have said that first. So if you see that C1, 1, 2, 3 becomes negative C1, 1, 2, 3, what does that mean? No? Well, we are not. It's only now we have one symmetry only. Yeah. So, what does that mean? If something is negative of itself, you guys are taking two. It has to be 0. Otherwise, how can that be? Is it end of the semester effect? What's going on? So this is 0. Now I want to say that forCijkl becomes negativeCijkl for when, let's put, when index 3 appears an odd number of times. If it is even, negative 1 times negative 1 becomes positive 1. But if it's odd, it's going to be negative, which would mean that for those terms, what does it mean? ThenCijkl for those terms will be 0, right? That's how those zeros appear in your elastic tensor. So to be specific, you don't see it?
No, it's negative sign.
Oh, that's a good point. So Q3S. Look at Q.
I didn't know this was coming first.
So we are looking at the symmetry. So we are thinking, okay, if we flip the axis, what happens? If the material is symmetric, you are looking at something that if you flip the axis, things stay the same.
I was thinking that this
No, so that's fine. Now, if the 3 is appearing an even number of times, negative 1 times negative 1 becomes positive 1, and we are good. So, what does that tell us? If we go back here, yes.
So that's C prime. So why can't C prime 1, 2, 3, 1, 1, 2, 3 equals C 1? So this formulation has to be C prime 1, 2, 3 equals the rest of it.
So no. Why? Because of, no, this is a good question. Please ask questions, because I sometimes I don't know what is not clear. So C1, 1, 2, 3, we want to look at the symmetry. And the symmetry implies that if you rotate, just like when we looked at isotropy, if you rotate, things stay the same. So then there is no C prime. No, symmetry is already built in. So let's look back. That's why I wrote this here. This is symmetry is already built in. This will never change. This will never change. This is for the most general case scenario. Now, if you have symmetry, if you rotate with that cube, you want to see what happens. You see that if you rotate, that component has to be 0.
So it should not symmetric if there are it doesn't.
Does it make sense? Yep.
First line is 1, 1, 2, 3,
No. So it has to be prime, but that should be equal to C1, 1, 2, 3 if you have this symmetry. I think this is Valerie's question too. So this should be C prime. We can start it with C prime. But to have this symmetry, this has to be equal to C1, 1, 2, 3. Otherwise, we don't have any symmetry. You are rotating it. What does then? When we implement the symmetry? So when I ask you what you remember before, let's think about the where is it now? You remember this quiz when I asked you, so what does it mean if it is isotropy? That means, so if you rotate it now about anything, and that's where we go at the end of this, but then C prime ijkl should be the same as C ijkl after rotation. Okay. Now in this particular case, the only symmetry you have is with this particular cube. That's just one cube.
Oh, we're saying it was
Yes, exactly. No, we are not testing for symmetry. So it's kind of, sorry if this was not clear. So we are considering different cases of symmetry. And the first one is if you only have one plane of symmetry. Does it? Yeah. It's probably this now. Yeah, I know. But I think it's fun to see what you have probably seen before differently, that how it actually looks. Okay. So, now what I wanted to do is to go back to this, and that's why I went through the pain of writing this. And for this case one, so case one I use red. Look at the ones which are 0. I just told you 3 has to appear an odd number of times, so that will be 0. This will be 0. Everything else stays the same, like C1, 1, 2, 1. This will be 0, this will be 0. This is still odd. This looks like it's also odd. These are even. This guy is odd. This is odd. I lose 8 constants. Now, if you don't have any other color, I don't know. You can just write which components are equal to 0. Just see 1, 1, 2, 3. So what did I call this? Plane of symmetry. Sometimes this is called monoclinic. So 21 constants will be reduced to 13. Because 8 are 0. Okay. Now it becomes more interesting. So the next case is when we have, instead of one plane of symmetry, 3 mutually orthogonal planes of symmetry. Right? So case 2. Three mutually orthogonal This is a very useful one. Wood, a lot of fiber reinforced composites fall into this category. So you can think about it as having 3 symmetries like the previous one, but having all 3 at once. Right? So what do you think will happen? Which coefficients will go 0? Think about it for a few seconds. If you have, instead of just one plane of symmetry, let me show you the nice picture from the book. If it looks like that, which is a very good and nice a lot of applications are like that. What would happen to your elastic tensor? Which elements would? Exactly. Is that something everyone can relate to? So if the same thing happens not only when you flip around xz but also xy and yz. So if you have one symmetry, you can think about it as one after the other. One symmetry, all the ones which have the odd repetition of 3, you have to set them to 0. Now if you flip it around the second plane, all the ones which have the odd repetition of 2 have to be 0. If you flip it one more time, it turns out that actually 2 is enough, because if you have 2, the third one also happens. So let's go back to your big matrix. Three planes of symmetry perpendicular. You know what this is, right? Mutually perpendicular.